right, welcome to the third video in this series about base 12 math, base 12 geometry, 360 degrees, and base 12 pi. And so what I was just doing actually was just counting the numbers. If you haven't already watched my first video, first of all, you should watch that because I'm going to be referring to basically all the things that I was talking about in those first two videos. So if you haven't watched that, you can just click on this link and go there first. But what I was just doing now was looking at this, value of pi that I've written on the wall in front of me here, and I was just counting the numbers to make sure I got it right. I wanted to just comment on the length of the number, and in base 10 there is 114 digits starting from the 9.B80. So what I was doing, I was just counting it in groups of 12 just to get the numbers like 9 times 12 and then plus 6. So that's up to 114. But what happened, what was quite interesting, is I counted along and I counted, so here's the beginning of the number. So I counted, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and I landed on a 1. So I just put a mark there to see, okay, and I make sure I was counting the right amount. So then I counted 12 again, and then I landed on another 1. Or no, I landed on a 2. Right, 1, right, then a 2. Yes, just checking. So I landed on a 2. Then I counted along and I landed on another 2, and then 3, 3, 4, 5, 5, and then a 6. And then it goes 6 digits, and then the last one is a 0. And I thought, well, what if I just kept this count going? So I went to the beginning again and counted 6 more in, and I landed on a 7. And then I counted another 12, another 7, another 12, another 12, another 12, another 12. You get this pattern, and then I land on a 0, and then it's 12 more to the final 0. So that's an interesting, unexpected pattern that I just discovered 5 minutes ago about this base 12 version of pi that you get when you divide the diameter of a dodecagon with its circumference or perimeter. So that's interesting. So I just wanted to share that with you. There's that pattern is inherent there. There's a lot of interesting things about that number. This is such a lot of uncharted new territory. And again, my intention with all this is simply to inspire you to look deeper yourselves. There's just so much. So what I wanted to do in this video is just go over a few little things about base 12 that I've noticed. And actually what I wanted to touch on first was the Fibonacci sequence. So obviously that's not the Fibonacci sequence. So there's that new discovery just 5 minutes ago. There's lots more to come, I'm sure. And to be honest, in a way, I've enjoyed working on this just myself, with this little discovery of my own, exploring it. But my mathematical knowledge is very limited. Obviously it's a huge subject, and I really believe that this value of pi, I'm going to share with you one of my dreams that I had actually right now at the beginning of this when I first was starting. It was a dream where I was at my elementary school, and I was standing by the flagpole that's at the school in the middle of the grounds. And around the base of the flagpole was a giant python, and it was writhing around the base of the flagpole. And I was standing there looking at it, and it had sort of a glowing, luminescent quality. And then all these small little snakes were sort of sprouting off of it, and they were slithering around, and some of them were eating their own tails, or they were eating each other and spinning around and sort of disappearing or slithering off. But a lot of little snakes were appearing out of the big snake. And so basically I was just standing there and looking at all this. And so I realized later in my interpretation, first of all, the pun there, the python, from this, what I would consider new version of pi, that is very obviously fundamental to mathematics. When base 12 math, base 12 geometry is established or accepted, or someone's working in base 12, from that large version of pi, or this new version of pi, will sprout all these other patterns and relationships within math that we don't see right now that will, be brought forth because of using a different version of pi. So that was my interpretation of the dream. I'm just sharing that with you if you're, I don't know, on the fence about making the effort to, engage in base 12 math to figure out what it is. I really do think, I've said this already, but I'll say it again, that there are things to be discovered in the realm of base 12 math, perhaps problems to be solved that currently remain unsolvable, but like say the Riemann hypothesis, something like that, perhaps tackling it in base 12, some sort of pattern that isn't currently visible may emerge. Okay, so I share that just as a, encouragement. I know these videos have a very simple, basic, amateurish quality to them. Just me standing here in front of a board, no fancy graphics or anything, but the idea is very simple and yet also has far-reaching implications. Again, that the universe has a base, and that base is base 12. And so along those lines, with that idea in mind, I'm going to write out the first 30 or so iterations of the Fibonacci sequence, and we're going to look at that from a base 12 perspective. So we're going to start with just 0, 0, 0. And what I'm going to do is write it out kind of like the odometer of a car, say. So again, the Fibonacci sequence, just if you're not familiar, although it's a very famous, well-known number, and you can, find out a whole lot more about it on the internet. We're starting with 0, then we're starting with actually 0, then 1, then we're adding 0 to the 1 to get the next number, 1, then we add the 1 to the 1, get 2, 2 to the 1, the next number is going to be 3, and then 0, 0, 5. I'm just going to write a little bit smaller here to cover as much ground as we can. 0, 0, 8. Now I'm going to do this in base 12. I'm just going to write it out quickly, and then we'll go over the details of what it is I want to show you. Okay, well actually I think that's far enough to get the point of what I want to say. It was basically this, and I think some of you may already be familiar with this, but I just want to share with you anyway, that you can see the pattern. We've got this double 0 up there, and then we go along here, and if we just count, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's one section of 12. And then we get this 0, 0 happening again. Again, I'm writing this all out in base 12 so you can see how it lines up in relation with 12. So again, starting there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to here. So this is a section of 12. And then you can see here, again, we've got 0, 0, 0, 1, 0, 1, 0, 2, 0, 3. It's repeating. So we have an overall repeating pattern right there of 24, which in base 12, we write it as just 20. Two groups of 12s, 24. So we have one section of, and then it repeats, and that's a section of 24, 20 in base 12. So what happens, what I noticed, what I was doing is I was writing all this out, all these sort of iterations of the Fibonacci sequence, just calculating them using a calculator, and I got this far. There's about 16 digits in there in that numeral, and that's to like 12 of these. So what I wanted to do was see what, if anything, happened after doing that again to get 24. I do this whole thing 20 times to see what happened with this column here, this third column. And what happens when I got to the end, and what you can do basically with Fibonacci, you can just be adding up those first few digits, carry the one, and then you can still do them all without doing the complete number. So I was doing that, and what I found was after another 20, this whole pattern repeated. This whole pattern, that third column, this column here, started repeating itself after 20 iterations. And I'm just wondering, perhaps after that has all done and we go 20 times, does the next column, with this, if you put all zeros along here, all the way down to there, does the next column repeat, and does that pattern just keep going? If we do that, does that go then by 20 and then that by 20? Is there some kind of pattern like that involved in the Fibonacci sequence? Which also, because I think people are familiar with the idea that the Fibonacci sequence is expressed in nature, part of my argument or my hypothesis or my idea that I'm presenting is that the universe or nature works in base 12, but this might be something to explore further, the idea that the Fibonacci sequence also works in groups of 12, and that you can see this, sort of 100 here, and 800, and there's also patterns within the pattern. There's this goes 1, and then there's an A there, then it goes 3, and then an 8, and then a 5, and then a 6. As there's lots of patterns within the pattern that are there for exploration. Again, that's just me taking a cursory glance. I think what would be interesting here is to see this pattern as the spiral and what's happening within the geometry of the spiral as this pattern really does a lot of spirals. It feels like this is the skeleton of the spiral, and that you can deviate around it. Again, the idea of empty space or sort of a thickness to the spiral is something I'd like to explore more myself, because that seems to be a lot of times people point out that in nature it's not exactly the Fibonacci sequence. It's close, but it's a little bit off to one side or the other. So obviously there's not just one type of spiral, but there's a skeleton or a base to the spiral upon which other spirals can rest. So just some ideas to throw out there. I wanted to share that with you. That's the Fibonacci sequence in relation to base 12. And so I'm just going to share one more thing, and then I'm going to wrap it up to keep this short. No more long videos, just some short ones to express new ideas. What I wanted to do was to talk about the diagram that I showed you for generating all 360 degrees, the one I have in the garage, and how as you go out to the edge, the circles that you have are getting, those big circles with the two little ones inside, they are, becoming more and more straight up and down with each other in relation to the center point, to the circumference. The circumference of the circle basically is getting flatter and flatter as you either frame it in looking at the circumference of the circle getting smaller in terms of like we're zeroing in, or getting larger and also looking at a smaller section. Either way you want to look at it, basically the side is getting flatter. So does it, and that's, I was surprised when I did all those calculations to find how quickly the angle inside of these circles here, as they line up with each other, gets to 179 degrees and a half and a quarter. So it's very quickly, we're in my garage and just another, across the alleyway, and down the street a little bit in terms of perspective or scale. we're getting really close to just a flat line between these, but of course we know it takes a long time to get there. Do we ever get there? That's the question. Is it possible to combine the edge of a circle with a straight line? Can they overlap? Is it possible for the edge of a circle, the circumference of a circle, to also contain a straight line? And this is where I really wonder about our definition of a circle, whether it's not limiting us. Right now we have the definition of all the points are equidistant from the center, and that's about it, really. I think it's important to also include in that definition that the points also have to be equidistant from the points on either side to create a symmetry within the circle. And what this diagram or this model represents is a new way of looking at it. Now here I'm drawing everything very loose, but these are those same circles put on their side. So here we are. So in the model that we had, this was the edge of the circle, and the degree lines were coming out here. But if we turn this, now we have the circumference of the circle going through between these 2 points. So we get to a point when these circles are actually stacked right on top of each other with no variation. The lines between these circles and the one above are perfectly straight. So what we have is a gap then going between these 2 circles. So I want to make sure you understand that the lines between these 2 here and these 2 here are perfectly straight. There's no bit of a curve one way or the other. And then the circumference of the circle is able, and I'm going to exaggerate a little bit, so it'll be coming through here like this and going like that. So we have the curve of the circle incorporated or sharing the space of a straight line going through. And this is where it really helps to keep in mind the idea of the scale involved, and that these, on the one hand, this is very small. On the other hand, that gap is very large when you're thinking of like giving this line here the value of like a dimensionless line, or just one step back from a dimensionless line where it has some kind of thickness or diameter, and yet it still is incredibly thin compared to the spaces between here. It just seems to me a little bit I don't say nonsensical, or it doesn't really make sense to say that we can't create a perfect circle somewhere in the scale between, say, the Planck length and the size of the entire universe. There's nowhere in there where a circumference of a line can overlap, or circumference of a circle can overlap with a straight line. It doesn't really make sense. I think our definition of a circle might need to include a thickness for the circumference, and that's what we're getting with this dodecagon. When you have the 2 circles, and then the dodecagon fits inside it, basically, very roughly drawn there, but basically straight lines inside the circle with the rings have an inner and an outer thickness, and then that circle can get very, very, very thin or squeezed together, and yet it still has the ability to draw a series of straight connecting lines inside of it. So that's something what I wanted to put out there, just to clarify that. And the last thing that I wanted to say was sort of the idea that right now, when you look at that diagram, it seems like an interesting diagram, but there's the expectation of, well, when do you fill in all those spaces? When does the circle actually become a solid line? In that diagram, you have all these radiating lines going out, and you have all these circles with this gap in between. And I would actually say there is no point. There's no then, and that idea or that realization that there's no point when that line becomes solid is just an acceptance of the fact that even though we see in the world around us solid objects, they're not actually solid, and they are full of gaps, full of empty spaces, and that It's actually just the fact that those spaces are so small, we can't perceive them obviously with our human eyes, and we don't experience them on the scale that we live. But now we know with our physics, be able to reach and see down into the very, microscopic level, that in fact everything's made up of atoms, and the atoms are made up of protons and neutrons and electrons, and these things have some sort of space involved in their relationship to each other. So this is what our numerals or our numbers are telling us. These continuous irrational numbers that go on forever are just reflecting the idea that actually, when empty space is what the universe is made out of, or is one of the qualities between everything, that is when we're dividing something up or taking a measurement, that needs to be taken. You can always divide empty space into something smaller. And so another example of that might be when we consider, the square root of 2, that length there. So when we're trying to figure out that length, and we start to say, well, it's, square root of 2 is 1.4, and then it just goes on. So what we usually do is we start there, and we measure, 1, and then we go 0.4, and then we're basically adding lengths together. But instead of looking at it as 1.4, now I don't remember what the square root of 2 is in base 10 or base 12, but just say, but we said we have our number, and it has, all these digits. Instead of putting our decimal point there, we should have it way down here, and that actually what we have is a huge number that is representing a tiny amount, and that this line isn't actually starting there and just a progression, but it's sort of floating. And so we have our 1 is divided into 10, and then our 0.4 is 14, and then 141 or whatever it is. So we have all these sections of line, and our lines are actually floating, and that all those little bits are just little bits floating in space with some empty space between them. So I don't know if I've expressed that idea very well, but that's what I'm trying to get across in terms of the new way of looking at irrational numbers, that they actually, when we're only just working with the beginning part of them, and the fact that they go on for so far is actually a reflection that they are reflecting a quality of the universe that we live in. Okay, so that's all I wanted to say for this video. That's just continuing with the ideas that I expressed in the first videos. Thanks for watching. That's it for now.